Plastic is everywhere. It's in the shirt, it's in this cup, it's literally in the air. And yet, we keep producing more of it. So the big question is, how do we deal with it once we're done using it? Ideally, through recycling. The most commonly used recycling methods are mechanical recycling and chemical recycling. Mechanical recycling sounds simple. You take the plastic, grind it up, melt it down, and then reuse it. But in reality, it's much more complex. One major challenge is that different types of plastics are often used together, be it as the label of a bottle or a shoe consisting of many different types of plastics. This situation can be somewhat improved by chemical recycling, which breaks the plastic's polymer chain down into its building blocks called monomers. These can then be reassembled into a new polymer. Unfortunately, these methods often take a long time, use lots of energy, and produce toxic byproducts. Both recycling techniques have serious downsides. Either they damage the plastics or they harm the environment. Meanwhile, over 1 million PET bottles are sold globally every minute, and most of them are used just once. Incredibly, in 2016, scientists found a bacterium called Ethyleneterephthalate, which is actually able to break down PET. With an enzyme called Petase, it cuts PET into its building blocks, similar to how our body digests food. Sadly, the Petase enzyme is still too slow and unstable for industrial use. Which is where my research begins. The main point of my master's thesis was developing methods in order to investigate the enzyme further. To do that, I first had to understand the plastic it breaks down. PET is a semi-crystalline polymer, which means part of it is crystalline. This part is tightly ordered and strongly aligned. The other part is amorphous, which means it's more disordered and therefore easier to break down. It's already known that Petase works better on the amorphous parts. Except nobody has seen this happen directly until now. To watch Petase in action, we start with preparing PET samples with both crystalline and amorphous areas. We start with a simple PET bottle, which we cut down into small pieces and then use an ultramicrotome to slice it into thin sheets. Next, we heat up the PET sample above the PET's melting point to erase thermal history. Then we slowly cool the sample down to trigger crystallization. When you look at the sample with polarized light, the crystalline areas start to glisten due to their birefringent properties. The amorphous areas, in contrast, look dark. They don't affect the light because they're isotropic. The second step is to prepare the enzyme. We work with two versions of Petase, the wild type originally found in nature and a faster mutated version called Fast Petase developed in 2022. To make the enzyme usable, we insert its reported genetic code into an E. coli bacterium. We let the bacterium produce the enzyme for us and then we crack the bacterial cell open to collect the enzyme. The third and final step is simple. We let the enzyme loose on the surface and watch what happens using an atomic force microscope. This microscope works like a tiny record player, except instead of music, it scans the surface on a much smaller scale to create an image of the surface. We scan the PET surface before and after enzyme treatment, with both the natural wild type and the engineered Fast Petase. Now we have confirmed microscopically the amorphous regions get degraded indeed faster than the crystalline ones, and the Fast Petase is indeed significantly quicker than the wild-type version. To understand how just 5 small mutations can make such a big difference, I ran molecular dynamics simulations. I found that the loop near the active site, which is the molecular structure used by the enzyme to digest PET, looks very differently in the two enzymes. In Fast Petase, this loop is more flexible, which might help it grab and cut the plastic more efficiently. I hope eventually we will be able to modify the enzyme to make it even faster, stronger and ready for industrial use. But for now at least, my master's thesis provides the foundation.